Right, thanks for having me. I do not know that much about proof theory, but I'm trying to learn. This will be, though, completely, well, somewhat different. So I'll try my best to explain the best of my abilities, but please feel free to interrupt me anytime and ask questions. So in some sense, there is no new mathematics in this talk. Indeed, the mathematics we're going to see were already known in the 60s. But still, there is some value from putting two and two together. And as you will see later, there was this problem in theoretical physics that also was open in the 60s and, well, remained open until very recently when we could show that actually, in a certain sense, there is only a negative solution to this problem if you do not at least modify the problem. So I'll have, well, okay, so this is a joint work with my two friends, Marios Christodoulou, who is actually here in Vienna at the Institute of Quantum Optics and Quantum Information. Yeah, next door here. And with George Sparling from my days in Pittsburgh. He's at the University of Pittsburgh. Yeah, so maybe I should say a few words about general relativity first. Feel free to stop me anytime because I know that this is not it's not expected everyone to have like training in differential geometry. So that's why I'll start with something scary, like a definition that when you first see it's difficult to parse and understand what it means. And so let me start from there. But you'll see, as you will see in the later slide, I will make things much more concrete. But very abstractly, when we are thinking about a Lorentzian metric, we start with a manifold M. So let me draw like a working picture for a manifold. Like for me, this will be a manifold. I'm sort of drawing it as if it is two-dimensional, but here it is more relevant to think of this manifold M as four-dimensional. So for the problems we're interested, it will be four-dimensional. And to talk about a Lorentzian metric, what you want to do is you want to, well, if you read what it says, you want to fix a section which is symmetric and signature 1,3 of a certain bundle. The only thing I've written in the board is this M, which is where this weird thing arrows. Let's try to understand what this means. So what this means is that, look, if you fix any point in the manifold, so let's call this point little p, you can look at the tangent space here. So the tangent space here, it's going to be a Euclidean plane, which is tangent to this. Think of it as a surface, but of course for us this will be R4 if the manifold is M4. And in the tangent plane, what objects do they live there? Well, what lives in the tangent plane are vectors. Vectors. So I may give you a vector. You can think of this as velocities of paths inside the manifold. So you have this vector. Let's call it V. And maybe you have another vector. Let's call it W. And when you have two vectors, one thing you may want to do is you may want to take the inner product of these two. You may want to take the inner product. Without any additional structure, you cannot take the inner product. So what this gadget allows you to do, it allows you at its point P, it allows you to lift a certain inner product that you can hit these two vectors with and get a value. So really, section means for every point in the manifold, I fix an inner product in the tangent space. However, the fact that it is the signature is 1,3, it makes this not exactly an inner product, but some sort of a weird inner product. So it's a weird inner product because you can have vectors whose norm is negative. You can have vectors which are non-zero and whose norm is 0. So Well, right, so 1, 3 means one direction is special with respect to the other 3. So it means, so formally, you'll see in the next slide, when I would make this concrete, the way you define it is that, well, these inner products correspond to matrices, because inner products correspond to matrices. And this matrix will have 1 negative and 3 positive eigenvalues. This is what it means. But intuitively, what it means is that locally you have 3 directions in which space evolves, and only 1 direction in which time evolves. And you can see this. So this is my point P. Now, locally here inside this cone, if I move, if the vector is inside this cone, it means I'm going with the direction of time. Right. If I'm on the boundary of this cone, it means that I'm light. Only light can travel on the boundary of this cone, and these are the past directions. And directions which are outside of the cone are things that I cannot casually reach. Maybe we can meet later. Maybe we can meet later, but I would not be able to go there in a causal way.
So, and why is that?
Causal way, sorry.
Is that a tensor product or is this a product?
No, it's a tensor product, and on top of that, I look at the dual space. Which thing? So it is specified by 16 coordinates in the case when the manifold is 4. I mean, maybe the easiest way is to, now that I gave you somehow, like, hopefully some intuition about how to think about this abstract thing, let's try to make it concrete so we can work with numbers. And the way to do that is to sort of, let's think of this as just being simply R4, which is not such a big, well, standard R4, I guess. But it's not a big issue because any 4-dimensional manifold locally looks like R4. So now here I'll be concrete, and this is how I will work from now on. Right? So my ambient manifold is R4, and a Lorentzian metric is given, and I'm very careful here with words. I'm not saying it is, I'm saying it's given. It's given by a smooth map. This map takes, which I'll denote as mu nu, and this map takes the point and maps it to a 4x4 matrix, and this assignment is smooth, okay? Now, for this to correspond to a Lorentzian metric, what we want is that this matrix at its point to be symmetric, and having signature minus plus 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 means that it has 1 minus and 1 negative and 3 positive eigenvalues. Norm. Yes. It's positive, yeah. Exactly, yeah, exactly. Precisely. Right. But there are also these weird directions where the norm is 0. Right? The light, exactly. Right. Now, okay, I said again that I'm careful with words. I'm saying is given, because you see, at each point, these are just a whole bunch of numbers. Like one of the things that you struggle, when you're an undergrad first year, you struggle with linear algebra, is that initially you identify, so let's say if I give you 3 numbers, 6, 3, and pi, so this is just a collection of numbers. It's not a vector. It's not a vector yet. To make it a vector, you need to say 6 E1 in a specific basis plus 3 E2 plus pi E3. If we identify this as some vectors in some vector space, now only after this identification we can think of lists of numbers as vectors. So this matrix here, on its own, is not really well. This assignment is not really a Lorentzian metric, but it is a Lorentzian metric if I specify coordinates in every tangent space in the manifold. That's why the way we usually write this matrix in a way that doesn't depend on fixing coordinates is like that. So now this is really the metric, These are the coefficients. And here, this is a covector, and this is a covector. And here, throughout this lecture, I will adopt the Einstein summation notation, which says the way you should think of it is that, right, my coordinates often will look like this. When I write that, I'm thinking of xi as ranging between 1 and 4, or I guess 0 and 3. 0 and 3. Right? So now this is this can, depending on what xi I plug, I get something concrete. But often what happens is that when I have a variable like mu up, and I have something here that has the mu down, whenever you have the same variable up and down, this means immediately that you have summation. It's a way of talking about this sum without constantly writing the S symbol. Right. It means the cotangent. So you have the tangent space, and then this has a dual, which is the cotangent space. Right? And you see it's cotangent because you take this and you hit two vectors with, and this gives you a number. So it acts on pairs of vectors. Okay. So let me give you an example, because sometimes I will write the matrix, sometimes I will write in this notation. So here's an example. So often I'll just be writing this. Okay, here I have t, but just I chose these variables. So usually I will write the x0, x1, x2, x3, right? But this I can alternatively denote it like that. And you see I do not have cross terms dx, dy, because all the off-diagonal things are 0. All right. Questions if you have. Okay, so now that we learned what Lorentzian metrics are, and these are just smooth maps, and what we can do with smooth maps is we can take derivatives. And when we can take derivatives, means we can write down differential equations. Right? And now this definition is not a definition from the standpoint of mathematics, it's more interpretational, I will explain. So if I give you the metric, you can derive it, and this gives you some other tensor that depends on 4 variables. Now, once you have this, you can sort of take sums, like trace in a certain sense, and this gives you this gadget. Okay, so this is called a Riemann tensor. Once you contract some variables, taking the trace, some sums, basically, this is what it means. You take some certain sums, diagonal sums, you get the Ricci tensor, and if you take the trace of this is a 2x2 matrix. If you take the trace of this is the Ricci scalar. The point I'm trying to make is that if you have this metric, all these quantities here are canonically associated to the metric. This means that the left-hand side of this equation, is basically some operator acting on the metric, and you can compute it. So the left-hand side, basically, it's all the information you have from the metric. Now, of course, you can compute it, and this will give you the right-hand side. And I mean, if you can put your units so that this 8 pi g over C4 will be 1 if you want, but we'll not do that. Let's take it out. The remainder will be a 2x2 matrix, which we call the stress energy tensor. And the way to think about this is the distribution of energy, I guess, in the entire universe. And the Einstein field equations tell you is that how the distribution of energy relates to the curvature, the geometry of the spacetime you're looking at. So this is not really a definition, because any Lorentzian metric you give me, I can plug it in this machine on the left-hand side. It will compute something, and then I'll remove these coefficients, and the remainder I will call it the stress energy tensor. So every Lorentzian metric, no matter how abstract it is, it corresponds to some stress energy tensor. But often physicists, I want to emphasize that physicists, often what they want to do is they want to fix some physically relevant collection of distributions for stress. They work backwards. So they fix something that that may be relevant for what they do, some distribution, and then they try to find solutions, they try to find geometries that pair with the stress energy tensor. Right, so think of it the other way, backwards. You fix a stress energy tensor that you care about, and then you try to solve that. And okay, of course, it's very difficult to find solutions, explicit solutions, but there is a whole industry trying to do that. Right? And maybe let me say that if you remember, back in the undergrad, some of the mechanics, you call it maybe mechanics, yeah. So Poisson's rewriting of the Newton's law of gravity is very similar to this equation. Here you have a whole bunch of second-order derivatives. These are second-order derivatives here. You derive twice. That's why from 2 you went to 4, right? You have some sort of on the left-hand side you have some form of second-order derivatives on some potential, and on the right-hand side you have the distribution of the mass here, the density, mass density. So it's very much. This is like a more refined version of that. You can think of it this way. All right. So now, where is the relevance of this with logic? Okay, so because I think this was like a crash course in. Some curvature, yes. It has to do with how certain geodesics. If you move according to certain geodesics, how much volume increases between parallel geodesics. It captures something like that. Yes. There is something interesting here. It may appear later. You see, all these three quantities are measures of curvature, right? This is all the information you can get, but then sometimes this is relevant in Einstein field equations. This is relevant. This is not needed, so you lose some information, I guess. And sometimes only this is relevant, which is some sort of average of. Okay, yeah. So maybe one more thing. I guess we're talking about physically relevant spacetimes. So it's a question: what is physically relevant? I said this is not a definition because it's a matter of interpretation what is physically relevant. So here's an example of a spacetime, an interesting example of a spacetime. Maybe some of you recognize it already, right? So this is one of the spacetimes that you can find closed time-like curves. Right, so you can you follow time. You just don't do anything. You just breathe, but while moving in a certain direction. And after some time, you come back where you started. Somehow, this is the idea of this universe. And the way to cook this up is to start with a stress energy tensor, where inside there you code some rotating dust. This sort of tries to push centrifugal force, push things out. But then you tune this with a certain negative cosmological constant with pullback things. And at the end, if you do this tuning finally, you get these closed time-like curves. And you may ask, is this a universe? Is this rotating dust plus negative cosmological constant? Is it physically relevant? Well, it depends who you ask. But one of the reasons why this spacetime is interesting is because it's Gödel discovered this universe, right? And this quote, is the universe rotating yet? So the story is, let me see what I wrote here. Yeah, so the story has it that in his later life, Gödel was obsessing with the possibility of a rotating universe after discovering, I guess, this solution. And the thing is that the observational data at the time were compatible with low rates of rotation. So and the quality of these observations kept improving continually all the way up until Gödel's death. And he would keep asking, is the universe rotating yet? And be told, no, it is not. So I think this is a quote from which book? Well, I'll remember it later. All right. So now how logic enters the picture is through this problem of observables. So what I want to do is I want to discuss a little bit this problem, right? So I'll start with a question, and you're familiar maybe with questions like that. For example, I may give you two graphs, and I ask you if these graphs are isomorphic, right? Or I may give you two Lorentzian metrics. So this is the constant metric. The entire manifold is constant, is the flattest metric. And then I give you some other metric where you see each component here depends on some variables. Some depend on x1, some depend on x2. It's a simple enough dependence, but you see some sort of waves happening. And the question is, it might be the case that these waves, the sine and cosine, the cosine you see there, for example, may just be artifacts of the coordinate system and nothing more. So the question is, do these truly represent different geometries? Or the difference is just a matter of choosing the appropriate coordinate system? To make this precise, there is a notion of a diffeomorphism. So if I give you a diffeomorphism, so a diffeomorphism for us, this is how I write it, but this is a very condensed way of writing the following. So if I write x eta is x eta of x tilde xi, what I really mean with this is that I have x0, which is the first coordinate in a coordinate system having 4 coordinates because I'm in R4, and this is really x0 that depends on 4 different variables. So I have these variables, and I have these variables which are different variables. They are x and y, if you wish, but it's more compact if I write it like that. So let's take it here. x1 depends on this. x2 depends on this, on the same, and you have x3 as well. So. So this is a function that it is smooth on these variables. This is so a diffeomorphism is a map from R4 to R4, which when you write it in coordinates, it's a smooth map. Well, I guess it's a smooth map that when you write that in the coordinates, you can actually derive and apply this formula here. So the diffeomorphism in the same way that if you have a bijection between the natural numbers, and you have a graph structure, you can pull it back and compare it with some other graph structure. Here you have a manifold, and on top you have a metric. Here you have another manifold. It's again R4. You have another metric. If you have a diffeomorphism, you can pull back this metric and then compare it with this metric. It's the same thing. So it's like pulling back a graph. You pull back the metric, and then you. But okay. If you forget about the chain rule, this formula would look very much like graph isomorphism. But you have to remember now that you have the chain rule because you differentiate, so you have to add some sort of terms. So think of it like a graph isomorphism. It's just that you have to remember there is some chain rule involved. So the question is, I give you two metrics. Can you tell whether they represent the same geometries or not? And this is a very difficult problem in general. Right? So it's difficult. In this case, it turns out they are diffeomorphic. So these waves you see there are actually artifacts of the coordinate system. And here, if some oracle came and told me how to make the change of coordinates, so you see this recipe is this. I give you a concrete version of that. If some oracle came and gave me the right recipe, what I can do, I can easily compute and check that this is a witness to the diffeomorphism. So what I do is I derive here, because I want to do the chain rule later. So I derive. These are the differentials. And then what I want to do is that I want to compute their squares. And then because of the way the first metric looks like, so it's like that, inside here, I want to plug these quantities. And once I do that, I hope to recover this matrix there. So, and you can see that you really recover this matrix because for example, these two here, there is this dx tilde 3 here, but there is also the dx tilde 3 here. So in this sum, this x tilde 3 will appear twice, and this is this contribution 2 here, for example. But the point is that deciding whether two of these are diffeomorphic, it's difficult because you don't have a priori an oracle with you. So you have to search in a space, infinite dimensional space of possible diffeomorphisms. Yes. Right. So here it is easy to see that it's not very difficult to see here that to tell whether it's a flat spacetime, but you don't know after the diffeomorphism if it's going to be, for example, complete spacetime, the complete flat, or some subsection of it.
Okay.
Right. Okay. You have so you can go at every point and check if there you are flat, and if you are everywhere flat, probably you can do it in a global way somehow. Check that you are everywhere flat. But this still doesn't mean that you have a global diffeomorphism with a flat Minkowski. Right. It's not only completeness; it's more. Actually, there is a uncountable collection of pairwise, non-diffeomorphic, flat spacetimes, which none of them embeds in the complete flat spacetime. So you got some sort of exotic flat spacetimes as well. So it's the local problem is always much more easy than the global problem. Right. Okay.
So here, spacetimes.
Yes. Well, when the manifolds are 4, they can, I guess, be. I'm not sure if they can have exactly boundaries. Maybe they can be sub-spacetimes of other spacetimes that have boundary. But here you have an open manifold, so. I have to think about if there is a way to sort of. I mean, you cannot find a diffeomorphism between this and the compact manifold.
Right.
So. Right. So there are some topological abstractions sometimes that can help you decide whether two things are not diffeomorphic. So it's something that I'm thinking about. You'll see now in the next, as we go further, it's of interest to study different collections of spacetimes. One very important collection for physics is the collection of what they call global hyperbolic. The spacetime we saw, Gödel's spacetime, is not globally hyperbolic, but well. I haven't defined what global hyperbolic is, but I do not know, and I do not think that it is easier to classify or to distinguish between globally hyperbolic spacetimes. All right. So now here's the situation. Let's get a global point of view, globally in the meta sense, that we collect all the spacetimes together in a collection. Right? And we have this sort of orbits. They're actual orbits because the diffeomorphism group of the manifold acts on these spacetimes by pullback. So you have these orbits, and two metrics in the same orbit correspond to the same physics. It's the same physics up to change of coordinates. This is what does it mean to have 2 points in the same orbit, right? And then we will call an observable. An observable will be a map from this collection to a polyspace, right? So often R is just the reals, but everything we'll talk about works for the arbitrary polyspace. So in particular, you may want to look at countably many measurements, right? So it's called an observable if it is invariant, meaning two spacetimes that happen to be diffeomorphic, represent the same geometry, will give you the same value. They're called observables because they measure quantities which are physical and not artifacts of the coordinate system. They're supposed to correspond to something like mass and total energy, something like that. That's why they're called observables. And the reason why these are important in physics is because in various classical quantization procedures, like canonical quantization, the way this works is first they find a complete set of observables. So maybe one observable is not enough because you have many distinct geometries that give you the same value. But a complete list would be to identify a collection of invariants that together they classify completely spacetimes in this family S, right? So if you give me two spacetimes, they are diffeomorphic if and only if they get the same values in this complete set of observables. You can use these observables to separate the spacetimes in the family. So classical quantization procedures, like canonical quantization, start by finding a complete set of observables, and then they seek to promote this to an algebra of operators on a Hilbert space. So this is how it's like a recipe for quantizing theories. And historically, Bergman started this program of trying to identify observables. So he defined observables as we did, functions of field variables that are invariant with respect to coordinate transformations. But 5 years later plus, he points out that this program of identifying and exploiting the observables has been underway for many years, but its execution is hampered by profound technical difficulties, which have not yet been completely overcome. Right? And this kept going. Here's a quote from Lee Smolin from the Perimeter Institute, 2001, who says basically that presently we can give a formal characterization of observables. What he means is the definition I gave, that they are invariant under diffeomorphism. This is the abstract, this is the formal. But we're not able to explicitly construct examples of such quantities. Such functions, we are not write down formulas for these things. And even more dramatic in the 2015, observables for full general relativity, and full they mean without assuming some special asymptotic symmetries or matter content, almost certainly do not exist. Right? And I want to say two things here. So this is a group of physics people, some quantum information people. It do not exist. Maybe it's like a little bit of too strong of a statement for in a group of people affiliated with set theory, right? They definitely exist. You can use axiom of choice. If you want, you can find complete observables using axiom of choice. Just pick from each orbit one thing, and that's it. This will be your complete. You have a single function that it is a complete set of observables. So what they really mean here is not exist. They mean exist in a way that it is useful to do physics. They mean that you can write down a formula allows you to compute things. Right? So this is one thing I wanted to say. The second thing I want to comment on is this without a special asymptotic symmetries or matter content. The reason they write that is that when the family of solutions is very, very restricted, then maybe there you can find complete set of observables. And here are some examples. Right? In the context of, so if you care only about spherically symmetric solutions, these are exactly the Schwarzschild solutions. These are black holes. So what you can do is you can take a certain integral. So I don't want to go now to what this integral is. These quantities here can be, these are vectors that can be extracted canonically from the G mu nu, from the metric, and the assumption that the spacetime is static. You have these special vector fields that tell you that things do not change in a certain direction, basically. Yes, right. So this integral here, what it does, it captures the total mass in this, and this total mass inside this universe that contains only this black hole and nothing else. And this mass is a number, and actually this number completely classifies Schwarzschild solutions. So mass is an observable that classifies this very restricted family of solutions, which are static, spherically symmetric solutions. Right, exactly. Yes, exactly. 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 So, okay, I will not go more into that. There are examples where you can find observables, many observables. In this case, here I don't want to go into that. Here you cannot classify everything, but in this very, very restricted setup, here you can find complete observables for static, spherically symmetric spacetimes. All right, but we called it the problem of observables. I mean, they call it the problem of observables because the thing is that, as I pointed out in the previous slide, they cannot find explicit functions that work for all solutions at the same time or all physically relevant solutions, all spacetimes coupled with a physically relevant stress energy tensor. Right? I mean, in all these cases, because here physics is involved, you have to understand also what is relevant for physicists. Because, as you pointed out, yeah, we are looking at specific collections here. So which collections we should focus on? Here, historically, we know that empirically we cannot find functions that correspond to invariants. Even more, we cannot find in no way we cannot find complete observables, but not even functions which are invariant, except maybe the constant map. Okay.
What counts as a formal characteristic?
Of what? Of?
What counts as a solution to the third thing?
So these are physicists. So explicit for them means probably something that you can write down a formula for it and use it to take integrals. Hopefully, possibly differentiating if you are in some fresh manifold.
I think the formal characterization. Okay.
This yeah. So this is the formal definition. This is the formal definition, okay. Which is also, you can say it also in the 58. This we define observables as functions that are invariant with respect to coordinate transformations.
Right, so that is a formal characterization.
Yeah.
Okay. But you also want that they classify, right?
This is the complete part. Yes. Yeah. Observables is just invariant. Oh, okay. Complete observables is also the classified. It's my color coding here, the red, the complete. Okay, and the point is that indeed this is the main theorem. Let me give you the public talk sort of version of it. Is that complete observables cannot be explicitly defined for full GR, for full general relativity. Cannot be defined explicitly in analysis. And the way I like to think of this is similarly as saying that if you try to do geometry of straightedge and compass, you cannot, using these tools, construct the cubic root of 2, right? But of course, here we're logicians, so we sort of have some our own opinions about what explicitly analysis means. For me, the way I'm going to define it, let me make it formal, so and you can agree or disagree if explicitly in analysis means this. But for me, it would mean Borel in this case. Or, I mean, one way to state it is, well, okay, I'll give you two statements and we'll see if this qualify as explicitly in analysis, okay? So here's the concrete statement, right? So let me read it first. So assume you have a collection of spacetimes that contains all vacuum solutions, and you say in the first bullet a vacuum solution. What I do is I affix a stress energy tensor to be zero, and then I look at the solutions only to that. So I'm restricting myself very much. I'm saying, look, let's first start with the solutions which you have no stress energy tensor, you have no distribution of mass at all. Just look at them. Here are all solutions. Here are all Lorentzian metrics. You can focus on various things, but let's carve out this part here, which I denote like calligraphic S empty. So the moment you contain this sector, basically what this theorem says is that this sector is pathological on its own. So whatever contains it, it's going to be pathological. Pathological in what sense? There is no map. If you try to find a map F on a polyspace, my notation for a polyspace is R there. Either it's not Borel, or it's not a complete classification. This is what it says. And remember, this is flexible, a polyspace, because you can take countably many measurements and combine them into a polyspace, right? Polyspaces are closed under countable products. So with countably many measurements, you cannot even classify even the case where you have zero stress energy tensor, right? But right, okay, and Borel, what Borel means, you talk about Borel, you need to have a certain topology first on this collection here. But remember, what is this? This is a certain collection of smooth maps from R4 to R16. And there are canonical Polish topologies there. Here, there are canonical Polish topologies. You can look at the C-infinity compact open topology. What's the basis of open neighborhoods for that? For every compact subset of R4, and for every number of derivatives, fix n, and for every epsilon, you have a fixed metric there, a fixed map here, and you look at all other maps that up to this nth derivative on this compact set they agree up to epsilon with this fixed thing. So on compact sets, you want agreement up to a finite amount of derivatives. These are the open sets. Once you have open sets, you can define Borel sets. And so this is the formal theorem. But if you do not like to think about topologies, actually, there is another way of stating that. You can say that it is consistent that ZF plus dependent choice plus no complete observables for this family exists. That's another way of saying that. So basically, this says that, remember, how to find observables, complete observables, one way is to use axiom of choice. Well, this tells you that you actually need to use axiom of choice. You cannot escape it in a strong way. Like even dependent choice, which is enough to do a lot of things in analysis, most of the things in analysis, constructive analysis, in a certain sense, even that is not enough. You need more than that. Right? Yeah. Yeah. Yes. And as I said, the tools using to prove this had been already developed in the 60s. I started this talk by saying that there is no new math here, just putting two and two together. So, and I think there is some value to this, because, I mean, once you know both these things, both the problem and the solution, it's not difficult to put them together, but for some reason, this problem was open since the 60s. And just to tell that how scientific communities work in isolation in a certain sense. I mean, maybe this is one thing to keep from this talk. I do not know it for a fact, but I do not think it is. I think it is. I think it is potentially, in the sense of Hjort-Kekris, potentially sigma 02. So it reduces to a sigma 02. I think, but I'm not. It's something. It's a work in progress, I would say. So what are you saying? You're saying to take the map from the space to the quotient space.
Yeah, no. Okay, so here all possible spacetimes. And I'm asking times, but then like all other spacetimes that become.
Yeah, you can take some.
Would it be always the case?
I don't know how you would formalize it if you fix first two of them. Like here all this the situation here is usually you won't have at least uncountably many different things in your family.
Okay. No, I guess. At least two less.
But you are in the right direction in the sense that there are interesting equivalence relations which are coarser. And there are even relations that are interesting for physics. For example, you can forget about pulling back the metric. Maybe what you want is to pull back only the causal structure, the structure of the light cones. So this is called conformal diffeomorphism. This is coarser than that, and this is another thing to study. It's another equivalence relation to study. It is causality. It's like trying. You preserve angles only. You preserve angles, but not lengths. You distort, but in a way that preserves lengths. Angles. You can try other things here to do as well. It's interesting. All right. So very brief about the proof. So the first part, the descriptive set theory part, I'll rush it because you probably know these things. This is a talk I also give sometimes to physics people. But so here the point is to find like first a more combinatorial setup where you cannot find complete observables with Borel, right? And we know already a setup like that. This is like you look at all bi-infinite sequences of zeros and ones, and the equivalence relation is the shift. So two bi-infinite sequences are equivalent if you shift one to match the other. Right? Now, it turns out that it's like a folklore, and this was used in the 60s to show that you cannot classify easily unitary representations of countable discrete groups which are not abelian by finite. Like this is this Glim, Efros, Maki, and etc. So this is the same thing used there, and this is the same thing I'm using here, right? So we know that there is no complete Borel observable here in a way to say that. So there is no Borel map taking values in a polyspace that you have if and only if here. The two things are equivalent if and only if this. You have equality there, right? And the proof here is to use a generic ergodicity, a certain 0-1 law. So the first thing you need to show, it's a lemma, that because this action of the integers here has a dense orbit, this produces the following 0-1 law. It tells you that if you give me a bare measurable, in particular Borel, if it's Borel in particular, it's bare measurable. So if you give me a Borel, let's say, okay, subset, which is invariant, either it has to be everything or nothing in a sense, up to a meager set. This is the 0-1 law you use. Once you have this lemma, then you can run like a cut in half peak argument. So assume without loss of generality that you have a complete, let's say, assume without loss of generality you have an observable, and then which is Borel. We will show that it's not complete, right? So let's say you pick this map. You can assume that the polyspace here, by taking a Borel isomorphism, that it is the interval 0-1. And what you do is you cut it in half. You look at the preimage of that and the preimage of that. Because of it's observable, meaning it's invariant, this gives you an invariant Borel subset, two invariant Borel subsets. One of them has to be comeager. Let's say it happened, the preimage of this would be comeager. Now what you do is you cut this in half. One of the two preimages will be comeager. And you keep doing that, and at the end you'll have an infinite sequence. You'll find something in the intersection here, whose preimage is comeager, right? So you found a comeager set that maps to a singleton, but you have a comeager set that maps to a singleton. A comeager set is partitioned in countable orbits, so you have at least comeager set cannot be countable in this case. So you have to have two orbits that map to the same place. It's a counting argument and a little bit of ergodic theory, the 60s. Right? So now we have this gadget here, we have this pathology. And now what we want to do to prove this theorem is try to shoot it into solutions, to various collections of spacetimes. Okay, this is the starting point. Right? I'm saying that here. So what we need to do is to prove what we want for some collection S we care about. We want to be able to take this pathology we have. This is the pathology. This is acting, and find a Borel reduction. So we want to find a way to associate a point here. So this is F. In a way that two things here are shifts of each other, if and only if the corresponding spacetimes are diffeomorphic. In fact, later, what we want to do is we want the range of this map to be inside this sector here, the S empty, the vacuum solutions, to prove the theorem I stated before. Okay. All right. So yeah. So I guess I have this definition. I'm saying that anytime you give me some collection of spacetimes where I can Borel reduce that there, let's call this family rich. Rich means you cannot classify it, right? So from now on, I'll say a family is rich means there is this pathology. You cannot really find complete Borel observables. Right? So now, if you just want to reduce this in the collection of false spacetimes, it's not very difficult to do that. Here is like a toy case. Let me do it. Right? In fact, this I can do it even in dimension 2. Right? So here's a family of spacetimes, even in dimension 2. Right, so these are the cosmological Friedman, Lemaitre, Robertson, Walker metrics. Here's how they look. They look very, very intuitive from if you're not familiar with gravity and you come from a Newtonian point of view. This looks very, very seemingly easy to understand because you have this sort of space-like foliation, I guess. So what happens here is that here's space. And what you do is that as time passes, you distort. I guess maybe here's a picture. You distort. So W is just any smooth map from the reals to the reals. Well, it has to be, I guess, positive, maybe something like that. Right? So it implements this distortion. They use it to study things like Big Bang or a big collapse. But you can also, to prove this, what you can do is that you can use it to code 0-1 sequences by expanding and contracting accordingly. So you can use some trick like that. So this is like a toy case of how to apply this gadget. What I don't like about this is that, in a certain sense, we cheat here because this W is also apparent in the stress energy tensor. So you can distinguish this space-time somehow. Already the difference is reflected in having different distribution of stress and energy. It might be more interesting to fix a certain stress energy tensor, fix one, let's say 0, for example, and try to see solutions that are on the same collection of, give you exactly the same distribution of stress and energy.
Well, it has to be a relation, right?
I'm saying if you give me, G mu nu like that, and some non-diffeomorphic G mu nu, let's put it tilde, and from that you plug it into the Einstein field equations, and you compute the stress energy of that, and from that you compute the stress energy. This reduction we do here factors through the stress energy. So we're sort of cheating. I'm saying, let's try to pick this thing like that when you compute them, these are actually equal. So let's make our life more difficult. Let's try to produce a Borel reduction, even in families of spacetimes, where this Borel reduction, you cannot factor it through the stress energy part.
So it's 0.
So for example, let's try to look at families where the stress energy is 0. Right? So these are the vacuum. Here becomes more interesting and more difficult. And this is the main theorem as well. And this is important to physicists because somehow this is, it tells to them, I mean, the way, I don't know if I have the quote here, the way they talk between them about this is what they're saying, somehow it's a pathology that underlies a theory. It has to do with the local degrees of freedom, which I don't know what this means, but it's how to talk about it. Like it's important to them because this means that the pathology comes from the local degrees of freedom in GR. Somehow this is how they frame it when they talk between them. I mean, I sort of know what they mean, but we can discuss later. It's not really. I don't have enough time for that. So, okay. So briefly now, how you do that? So you have to find a certain family of vacuum solutions where you can do the same trick. right? And there is this very interesting family of vacuum solutions, which are the gravitational plane waves. And here's how they look like. So here you see the variables are u, v, very suggestively, x and y, because you sort of have shifted the coordinate system. You have x and y are still space-like, but you have picked one space coordinate and one time coordinate, and you have mixed them to make two light coordinates, uv. So you should think of u and v trajectories as moving in the direction of both of them in different directions in the light cone, orthogonal sort of direct, exactly orthogonal, but I mean these are light-like vectors, so the norm is 0, so they are orthogonal with everything in a certain sense, but they are in directions that light moves. Right? And in this coordinate system, it's easy to explain, not explain, but write down these solutions. So you have this, you say this 1 and 1 here, the fact that you have 0 in the diagonal and 1 and 1 here reflects the fact that these are light-like directions. And you have this function here, and you know that this represents a vacuum solution if you satisfy this differential equation. 2 derivatives in x, 2 derivatives in y is 0. Great, yeah, thank you. Maybe give me, I'll use two minutes from this. Right, and the idea here is to do an appropriate coding. So we have freedom to choose this accordingly. Of course, here you could just place a function that depends on u. But if you don't put x and y, it turns out that all these are diffeomorphic with a constant, with a flat one. So you have to play a little bit around. So you have to find a way to code it on this part. Okay, I guess you find a smooth version of the zeros and ones. You feed it inside this formula, and now you hope for the best. And indeed, it's easy to show that if you give me two alpha and beta that are shifts of each other, then that this will be diffeomorphic. This is easy to see. The difficulty is the other direction. Give me alpha and beta, and go compute at the map at the space times. They look different in symbols, but maybe they are different. The difference is just an artifact of the coordinate system. So you have to make sure that it comes from the geometry. This is difficult. So if you try to brute force it and try to write down what you need to prove, you come up with this system of equations, which I tried for like a week and a half to solve. And one of my collaborators saw me at the end and was laughing at me. And it turns out that there is a more smart way of going about it. So you have to employ what is known as the killing symmetries. So each space-time may have some symmetries. Sometimes you have these sort of continuous symmetries, smooth symmetries. So killing vector fields are vector fields in which if you move the metric, it doesn't change. And what happens is that if you have two geometries, which are diffeomorphic, which are diffeomorphic, killing fields from here have to move there. And it's much easier to work with killing fields, and you from that you see that if these two metrics are diffeomorphic, the change of coordinates has to look like that, and from there you do the rest. And I don't have time for the rest, but the point here, let me leave it at this slide, just that. So it seems that here invariant descriptive set theory may say something. Because if the problem was, if you wanted to quantize gravity using concrete observables, maybe, and this doesn't work, maybe what you can do is you may try to reduce this to some gauge of the unitary group. So try to find some sort of equivariant forms of quantization. And here maybe invariant descriptive set theory may help you coordinate what is possible and what is not possible. I'll stop here.